All right, hello everybody. In this video, we're going to take a look at how to sketch the graph of f at x equals x minus 1 over x squared minus x minus 2. And we're going to take a pre-calculus approach here. That is, we're just going to look at the overall shape of the graph of this function and not concern ourselves with too many details. Now, in order to sketch the graph of this function, we're going to look at several of its characteristics, including its domain, intercepts, asymptotes and holes, and intervals over which it's positive or negative. But before we do that, we'd really like to see this function in factored form, because that will make it easier to determine some of those characteristics that I just mentioned. So if we look at our numerator here, x minus 1, it does not need to be factored. But our denominator, x squared minus x minus 2, can be factored, so let's factor that. We have a trinomial here. Coefficient of x squared is 1, so we're just going to look for two numbers that multiply to negative 2 and add to negative 1. And those numbers are negative 2 and 1, so our denominator can be rewritten as x plus 1 times x minus 2. So there's our function in factored form. So let's look at some characteristics, starting with domain. Well, if we look at our function in factored form here, notice that we can use any x values we want with a couple of exceptions. That is, we cannot use x values that make the denominator work out to 0 because we cannot divide it by 0. And those x values would be negative 1 or positive 2. So our domain is x is an element of the real numbers such that x does not equal or cannot equal negative 1 or 2. And that's our domain. So we can now move on to talk about the intercepts for our function, starting with the x-intercepts. Now, x-intercepts are points on the x-axis, therefore those points have a y-coordinate of 0, so we need to find the values of x that make this function work out to 0. So we can set it equal to 0, we can multiply both sides by this denominator, which of course on the right side will still give us 0 because we'll have 0 times the denominator. So we just have x minus 1 equals 0, and that means that x equals 1. So that's our x-intercept. X equals 1. At a value of 1 on the x-axis, we do have an intercept. Moving on to the y-intercept, these are points on the y-axis, so they have an x-coordinate of 0. So we can find the y-intercept here by setting x equal to 0, and that gives us negative 1 over negative 2, which simplifies to 1/2. So we have a y-intercept of 1/2. So there are our intercepts there. And we'll move on to asymptotes and holes, and we'll start with the vertical asymptotes. Now, vertical asymptotes occur at x values that make our denominator work out to 0, provided they don't also make the numerator work out to 0. Now, in this case, we don't have any common factors between the numerator and the denominator, so that's not going to happen. If we did have a common factor in the numerator and denominator there, we'd actually have a hole, but we don't have that situation here. So we don't have any, but we do have two vertical asymptotes, one at negative 1 and another at 2. So the equations of those vertical asymptotes are x equals negative 1 and x equals 2. Now, for horizontal asymptotes, we need to compare the degree of the numerator of our function to the degree of the denominator. Now, in the numerator, we have a degree 1 polynomial. In the denominator, we have a degree 2 polynomial. And since the degree of our numerator polynomial is lower than the degree of our denominator polynomial, we're going to have a horizontal asymptote of y equals 0. And that will always happen when the degree of the numerator is lower than the degree of the denominator. And the reason is because as x approaches infinity or negative infinity, we get a value for this function that's closer and closer to 0, mainly because the denominator is growing much more rapidly than the numerator, either in the positive or negative direction. All right, so our horizontal asymptote is y equals 0, and let's move on to our oblique, or specifically our linear oblique asymptotes. We'll get these when the degree of the numerator is exactly 1 higher than the degree of the denominator. That does not occur in our function here, so we have no linear oblique asymptotes. And we already briefly talked about holes. Holes will occur when we have a common factor between the numerator and denominator of our function, and we do not have that here, so our function has no holes. All right, one more thing to talk about before we go and try to sketch the graph of this function, and that is we need to look at where the graph is positive and where it's negative. That is, where our function is greater than 0 or less than 0. So how do we do that? Well, we usually use a table, and we're going to look at several intervals, and on each interval, we're going to check out the sign of our function f at x. Now, how do we come up with the intervals for this chart? Well, we need to include x values at which the function could possibly change from positive to negative or vice versa. So we'll want to include our x-intercept value here, but also our domain issues, which in our case here are where we have vertical asymptotes, because our graph could change from positive to negative or vice versa at either those vertical asymptotes or x-intercept. So we'll just go in order, starting with the lowest number of those, which is -1, and we'll look at all x values below -1. We'll then look at the values between -1 for x and the next highest x value here, which is 1. So everything from -1 to 1. We'll check out the interval from that x-intercept, which is at 1, to our next vertical asymptote, which is at 2. So from 1 to 2. And then we'll look at everything above an x value of 2. So those are our intervals. And once again, the numbers that you see here come from the x-intercepts as well as the domain issues, which in our case are vertical asymptotes. All right, so let's start by looking at the sign of our function here on the interval x values less than -1. So let's just pick a number that's less than -1, perhaps -10, and sub it into our factored form here. Now we don't need an actual value, we're just interested in the sign of this, so we can really just look at the sign of each factor individually. And if we sub, say, -10 into x minus 1, we'd get a negative. If we sub -10 into x plus 1 here, well, that factor would be negative, as would x minus 2. If we subbed in -10 for x, that factor would be negative. So for -10, we have a negative divided by a negative times a negative, which would give us a negative. So any x value below -1 is going to result in our function having a negative value. Now, if we look at the next interval here, from -1 to 1, well, we can choose an x value in that interval, say 0, sub it into our function in factored form here. 0 minus 1 is going to be negative, 0 plus 1 is going to be positive, and 0 minus 2 is going to be negative. So in that case, we have a negative divided by a positive times a negative, which is really a negative over a negative, and that's positive. So x values between -1 and 1 will give us positive results for our function. Moving on to the interval from 1 to 2, if we sub a value between 1 and 2 in for x, say 1.5, what do we get? Well, we'll have a positive in the numerator. Our x plus 1 factor will end up being positive if we sub in 1.5, and x minus 2 will be negative. So you have a positive divided by a positive times a negative, which is going to give you a negative result. And lastly, x values greater than 2, well, we're going to get a positive for each of our factors here, which is going to result in a positive value for our function. So that tells us where our graph has positive values and negative values, and now we have enough to do a pretty decent sketch of this function's graph. All right, so the first thing we'll do is we'll just kind of summarize all of this information at the top of the screen here. Our function is x minus 1 over x squared minus x minus 2. There's our domain. We have some intercepts, x-intercept of 1 and a y-intercept of 1/2. For asymptotes and holes, we have a couple vertical asymptotes, one at -1 and the other at 2. Those are the equations there, x equals -1 and x equals 2. Our horizontal asymptote at y equals 0, and we have our intervals over which our function is positive and negative. So let's draw the graph of this function. And first, we'll get all of this information onto our graph. Now, we know that our domain is x is an element of the real numbers, but x cannot equal -1 or 2. So keep in mind something's going to happen at those values. We know that it's a vertical asymptote in each case there. But we have an x-intercept at 1, so we can plot that. And we have a y-intercept of 1/2 right here. We can plot that. We have our vertical asymptotes, one at -1 and the other at 2. So we can draw those in. Now I've drawn them in red here, just as a reminder that I cannot draw a graph passing through those. Okay, they are vertical asymptotes. They're points, or they're x values at which we'd get division by 0, and we cannot have that, so the graph is not going to cross through them. So I like to draw them in red to remind myself of that. We have a horizontal asymptote of y equals 0. I'll draw that in green because it really just describes the end behavior of the graph, what the graph does at the ends. So if I do end up crossing that that horizontal asymptote at x values that are not large, that's perfectly acceptable. And now it all comes down to the positive, negative intervals. And we know that when our x values are lower than -1, our graph should be negative. So here's an x value of -1. And as long as we're to the left of that, our graph should be negative. But we also have to follow our asymptotes here. So the graph has to be down in this region because it has to be negative, but we have to follow this horizontal and this vertical asymptote. And if we do that, we're going to get a curve that looks like that. Now let's move on to the next interval here, from -1 to 1. Well, from -1 to 1, our graph has to be positive. And we also have to pass through these 2 points, and we have to follow this asymptote here at -1. So we're going to end up coming down like this, keeping the graph positive. We're going to go through that point there, and we're going to hit our x-intercept here. Okay, now notice that x-intercept is right on that horizontal asymptote. That is not a problem. Also keep in mind, we don't have to kind of move our graph towards that horizontal asymptote in an asymptotic kind of way here, because we're not talking about large x values. That horizontal asymptote really only kind of kicks in the far left and far right of our graph. So we'll come in from above here along the asymptote, hit our point and hit our point, keeping the graph positive. But then from 1 to 2, our graph goes negative. So from 1 to 2, for the x values, our graph will then go negative, but it still has to follow that asymptote, so it'll end up looking like that. So the curve that we get looks like this. Positive from -1 up until 1, follows the asymptote here, and then negative from 1 to 2. And last but not least, when x values are greater than 2, our graph has to be positive, so it has to be up here, but it also has to follow our asymptotes. So we get a curve that looks like this. And that is our final graph. Now, if I just take away those asymptotes, you get a better idea of what this graph looks like without all the other clutter. And that is it. The graph of the function f at x equals x minus 1 over x squared minus x minus 2.